Greetings and welcome. It's time to elevate. Strap in, this is going to be a good one, so get your popcorn ready. In the grand theater of the cosmos, stars are the main protagonists. Among them, our sun, a seemingly constant beacon of light and life, holds its own mysteries, dancing to the rhythms of magnetic forces unseen. Much like an antiquated compass, gone awry in the throes of unseen influences, the magnetic poles of the sun undergo a dramatic and perplexing dance. They reverse. This phenomenon, not merely a theatrical cosmic display, has profound implications that ripple across the solar system, touching the protective bubble around Earth and beyond. Each flip in the solar magnetic field begins a new chapter in understanding this celestial giant. Just like the Earth, the sun has two poles, the magnetic north and the magnetic south, which flip about every 11 years. Every 11 years, the poles of the sun weaken, and then they flip and emerge with much more energy, but with opposite polarity. The sun's last pole reversal occurred in 2013, and is due for another pole shift this year in 2024, and again in 2035, and so on. Magnetic pole shifts are a regular occurrence for the sun. The Earth has undergone magnetic pole shifts as well, but the cycle of the Earth's magnetic pole shifts are many hundreds of thousands of years in between. The Earth's North Pole has been on the move for a while and is currently accelerating. The Earth's magnetic North Pole is moving from Canada to Siberia at about 50 to 60 kilometers per year, but things transpire differently on the Sun, our celestial giant, the ruling object of our solar system. The story of the Sun's magnetic reversals is not just about the transformational loops of plasma on its surface, but a narrative that redefines the boundaries of human understanding of stellar dynamics. This narrative choreography, where invisible forces dictate a ballet of ionized particles across a 93 million mile stage, raises an array of intricate questions. How does such a reversal happen? Why does it occur with the rhythm it does? And what can it teach us about processes both stellar and planetary? As we venture into dissecting this intricate event, we dive deeper into the heart of heliophysics, uncovering layers of interactions that tell us more about our own place within the solar system's tapestry. If you are enjoying our content, please like and subscribe to be notified of our future uploads. The Sun's Magnetic Mysteries, an introduction to the study of the sun. The story of solar magnetic fields is a story written in the language of physics, translated through the machines and minds of astronomers, and decoded in the annals of scientific journals. But its essence lies in its universal impact, stretching beyond the confines of academic discourse to influence everyday life. Understanding the sun's magnetic pole reversal is to peel back a layer of the cosmic onion, revealing not just the workings of a star, but the fundamental processes that govern the universe. Understanding solar magnetism. Solar magnetism, elusive and dynamic, is the invisible hand sculpting the solar atmosphere's extensive features. It springs from deep within the sun's convective zone, where boiling motions of ionized gases generate electric currents. These currents, flowing through a plasma, the state of matter composing the sun, give rise to vast magnetic fields. Magnetic fields are not just abstract constructs. They are observable, quantifiable entities that stretch across thousands of miles, guiding the solar winds and dictating the architecture of the heliosphere, the vast bubble that encloses our solar system. Advanced computer simulations and observational data converge to provide a detailed portrait of these fields, how they arise, evolve, and eventually culminate in the dramatic magnetic reversals. By studying these simulations, scientists can predict not only when a reversal will occur, but also gauge its potential impact on space weather, which affects satellite operations and communication systems on Earth. Historical context of magnetosphere research. Unlocking the secrets of the sun's magnetosphere did not occur in a vacuum. It is the culmination of centuries of observation and innovation, beginning with the early astronomers who first turned their gaze skyward to record sunspots. The evolution of magnetosphere research mirrors the broader history of science, characterized by bursts of brilliance, patient observation, and the gradual building of a comprehensive scientific understanding. Illustrated here, a timeline tracks significant milestones, from Galileo's first telescopic observations of sunspots to the modern satellite missions that monitor the sun's magnetic field in unprecedented detail. Each discovery added a piece to the puzzle, bringing clarity to what was once considered an impenetrable mystery. The delineation of the solar magnetic field began in earnest in the early 20th century with George Ellery Hale's observation of magnetic fields in sunspots, which provided the first clear evidence that the sun was a magnetized object. This revelation opened new pathways in solar research, setting the stage for the engagement with phenomena like solar flares and magnetic loops, previously unexplained curiosities. The sun's magnetic field, an overview. Conceived in the seething plasma of the sun, the magnetic field is as changeable as it is enduring. Here, we explore the basic structure of the sun's magnetic field, tracing its path from genesis to reversal, and delineate the forces that shape it, stretching into a heliospheric veil that guards our solar system. This visual represents a cross-section of the sun, illustrating how magnetic fields emerge and evolve. The interaction of these magnetic fields with solar material gives rise to spectacular phenomena like solar flares, which are essentially magnetic storms on the sun's surface that can release vast amounts of energy. The sun's magnetic field is generated in its interior, where the heat of nuclear fusion creates a boiling sea of charged particles. Through a process known as the dynamo effect, these moving charges generate and maintain a magnetic field. This field is not static. It evolves in a cycle dictated by the internal dynamics of the sun. As the solar material moves, it drags the magnetic field along, leading to periodic reversals of the field's polarity. Mechanics of magnetic pole reversal. At the heart of the solar magnetic reversal is the dynamo theory, a complex interplay between fluid dynamics, magnetic fields, and nuclear fusion at the sun's core. This section dives into the physical processes that drive this astonishing phenomenon, unraveling the scientific threads that weave the intricate tapestry of solar behavior. Here, a dynamic computer simulation displays the tumultuous period of a magnetic pole reversal, where chaotic magnetic lines twist and snap, eventually reconfiguring in opposite orientations. This simulation provides crucial insights into the timing and nature of magnetic shifts, serving as a vital tool for researchers. Understanding the mechanics of pole reversal is essential for predicting the sun's magnetic behavior and its effects on space weather. The process begins with the intensification of magnetic fields in the solar interior. As these fields become more tangled and complex, they resist the orderly pattern of a stable magnetic field. Eventually, this complexity reaches a tipping point, causing the magnetic poles to weaken, collapse, and finally reverse. This reversal does not occur instantaneously, but is rather a gradual transition during which the global magnetic field becomes highly disordered. During this period, the usual bipolar magnetic structure is fragmented into multiple smaller magnetic fields, all pointing in different directions. As the field eventually simplifies, it settles into the new orientation with reversed polarities. Measurement and monitoring techniques. The surveillance of the sun's magnetic field is not merely an academic exercise. It is a vital part of our space weather forecasting infrastructure, aimed at protecting technology on Earth and in space. This section explores the sophisticated technologies and methodologies that scientists use to keep a watchful eye on our dynamic sun. This image showcases various ground-based and space-borne observatories dedicated to solar observation. Each is equipped with specialized instruments designed to measure magnetic fields, capture solar flares, and track sunspot activities, providing a comprehensive view of the sun's ever-changing magnetic landscape. Techniques for measuring the sun's magnetic field range from spectroscopy, which analyzes the light emitted by the sun to detect magnetic fields, to helioseismology, which examines sound waves within the sun to infer details about its internal structure and dynamics. Additionally, satellites such as the Solar Dynamics Observatory, SDO, and the Parker Solar Probe offer unprecedented views of the solar surface and corona, capturing data that is essential for understanding magnetic field reversals. These tools are not just passive observers, they actively engage with the data using algorithms and models to predict solar activity. This predictive capability is crucial for mitigating the effects of severe space weather events that can disrupt satellite communications, damage power grids, and pose risks to astronauts. The solar magnetic field reversal is intrinsically linked to the sun's 11-year activity cycle, known as the solar cycle. This section discusses the cycle's phases and their implications not just for the sun, but for the entire solar system. This graph illustrates the peaks and troughs of solar activity over several cycles, highlighting the regularity and variability of solar phenomena associated with magnetic field reversals. Each peak corresponds to a period of maximum solar activity and magnetic flux, which includes an increase in sunspots, solar flares, and coronal mass ejections. The solar cycle affects everything from the auroras on Earth, spectacular light shows caused by solar particles interacting with the Earth's atmosphere, to the stability of the solar system's heliosphere, which shields us from galactic cosmic rays. Understanding this cycle allows scientists to predict periods of intense solar activity, which are crucial for planning space missions and protecting our technological infrastructure. The implications of the solar cycle extend beyond just scientific curiosity. They play a critical role in our preparedness for space weather events, which can have profound economic and safety impacts on our technology-driven society. The journey to understand the sun's magnetic field has been marked by numerous scientific milestones. This section highlights some of the pivotal discoveries and technological breakthroughs that have shaped our understanding of solar physics. This timeline visualizes key milestones in the field of solar magnetism, from the first detection of sunspots to the latest advancements in solar observatory technology. Each milestone represents a leap forward in our ability to measure, understand, and predict solar magnetic activity. Significant breakthroughs include the development of the Zeeman effect, which provided the first tools for measuring magnetic fields in sunspots, and the launch of the Helios satellites, which for the first time allowed scientists to study the solar wind and its magnetic properties directly. More recently, missions like NASA's Parker Solar Probe have ventured closer to the sun than any previous spacecraft, providing invaluable data on the solar corona and its magnetic fields. These milestones are not just historical footnotes. They are stepping stones that have led to a deeper understanding of the sun and its influence on our solar system. The effects of solar magnetic shifts ripple across the solar system, influencing everything from the surface of planets to the outer reaches of the heliosphere. In this section, we explore the wide-ranging impacts of these magnetic reversals. This section illustrates the various effects of space weather, driven by solar magnetic activity, on Earth's atmosphere and technological systems. It highlights the interconnectedness of solar and terrestrial phenomena, underscoring the broad impact of solar magnetic shifts. The most direct impact of these shifts is seen in the increase in solar flares and coronal mass ejections that accompany the solar maximum. These events can lead to geomagnetic storms that disrupt radio communications, damage satellites, and even cause power outages on Earth. Moreover, the increased solar wind pressure can compress Earth's magnetosphere, altering its shape and effectiveness at shielding us from cosmic rays. Beyond Earth, magnetic shifts can affect the surfaces of other planets and the structure of the heliosphere, influencing the environment through which all spacecraft travel. Understanding these impacts is crucial for the planning and operation of interplanetary missions. Solar activity governed by magnetic dynamics has implications that extend beyond the immediate effects of space weather. This section discusses the broader implications of solar activity, particularly in the context of climate and interstellar exploration. This infographic details how variations in solar output, modulated by magnetic activity, can influence Earth's climate systems. While solar variations are not the primary driver of climate change, they can influence climatic patterns and should be considered in the broader context of Earth's climatic interactions. In terms of space exploration, understanding solar magnetic activity is crucial for the safety of astronauts and the success of missions to other planets. Solar radiation, influenced by magnetic shifts, poses a significant hazard in space, and managing this risk is a key challenge for extended human presence in space. Furthermore, the study of the Sun's magnetic field also provides insights into stellar and galactic processes. By studying our own star, we gain knowledge applicable to other stars and even insights into the magnetic fields of galaxies. Looking ahead, the study of solar magnetic fields is poised to enter a new era of discovery. This chapter outlines the future directions and technologies that will drive the next generation of solar physics research. In this section, let's imagine the next generation of solar observatories, both in space and on the ground, equipped with cutting-edge technologies designed to provide even more detailed observations of the solar magnetic field. These future missions will likely employ artificial intelligence and machine learning to analyze vast amounts of data, offering new insights and more accurate forecasts of solar activity. Future research will focus on improving our understanding of the solar dynamo, refining our models of solar behavior, and enhancing our predictive capabilities. This will involve not only more detailed observations, but also more sophisticated simulations that can mimic the complex interactions within the Sun. As our technological and computational capabilities grow, so too does our ability to understand and anticipate the Sun's behavior. This will lead to better space weather forecasting, improved climate models, and safer space travel. The journey into the heart of solar magnetism is far from over. Each magnetic reversal of the Sun opens new questions and provides fresh data for scientists to analyze. As we stand on the precipice of new technological advancements, our understanding of the Sun is set to expand dramatically, promising revelations not just about our star, but about the fundamental processes that influence the entire cosmos. This artist's rendition captures the dynamic and complex nature of the solar magnetic field during a reversal. It serves as a metaphor for the ongoing quest for knowledge, a reminder that in the vastness of space, our star's mysteries are yet to be fully unraveled. The story of the Sun's magnetic mystery is a testament to human curiosity and ingenuity. From the first faltering steps taken by early astronomers to the sophisticated space missions of today, our quest to understand the Sun's magnetic behavior has been a driving force in the development of science. As we continue to watch, learn, and wonder, the Sun will no doubt keep offering new mysteries for us to solve, beckoning us ever deeper into the secrets of the universe. Thank you so much for joining us on this deep dive into understanding the Sun's pole reversals of its magnetosphere. We hope that you enjoyed our content. Like and subscribe to be a part of our awesome community and become an elevated one. Until next time, my friends, stay electrified, stay vitalized, and stay elevated. You are all made of stardust. along with everything else in the vastness of the universe. You are all amazing in every way. So the next time you sit and watch the sun rise or set, remember, that is where we came from, and none of this would be possible without our sun. If you'd like to see more of our content, please click on one of the following videos on the screen and we'll see you there.